Hi, we're talking about the 4 types of motion. The first one is linear or straight line motion. If the frog applies a force to peso, then he'll move straight up or sideways. In any case, it's always a straight line. Here's an example of linear motion. This Beyblade spins quite rapidly when I pull the rack. Second type of motion is reciprocating, where we're moving in a straight line but backwards and forwards, like this. Quasi's actually sitting on a rack, which is like a gear folded flat. You can see lots of teeth. And here I have a pinion. So if I put the pinion on the rack and I spin the pinion, Quasi moves up and down. That's called reciprocating motion. The third type of motion is circular. Here I have a wheel and an axle, and you'll notice that the wheel can spin around. I need something to hold the wheel. It's called a bearing. In this case, it's just a hole in a piece of plastic, but works okay. Which means little dude here can hop on there and off he goes. Little motors like this are excellent at making circular motion. When we put some electric wires on the 2 terminals, this shaft spins around quite quickly. Here's the 4th type of motion, called oscillating. Here we have a wrecking ball. Imagine it's held at one end. This would be called the fulcrum or the pivot. So as it swings backwards and forwards, if I traced on the table, you would find not a straight line, but a part of a circle. It's called an arc. So oscillating motion is backwards and forwards in an arc, and off goes Chuggington. Here we see 2 pieces of Lego. One of them's oscillating. It has a pivot here, and it's moving backwards and forwards in an arc. If I change where the pivot is to there, is it still oscillating? It is, but it's quite useful now. It would probably be called a lever. Complicated machines can be broken down really into simple machines, and there's only 6 of them, and they've been with us for a long time. Let me show you. Number 1, you'd know wheel and axle. It's a lot easier to move heavy loads with a wheel and an axle. Number 2, inclined plane. This is a flat plane, now it's inclined. If we have Star Wars guy and we need to get him quickly out of a spaceship, then we can, looking from the top, slide him down, which is much better than dropping him straight down. Number 3, wedge. If we have Ninjago guy that needs to get up onto a roof, then we could use something as simple as a wedge. If I took 2 of these wedges side by side, like this, then it would still work, but it would be more common to find this kind of wedge on the edge of a blade. So this is a 2-sided wedge. Number 4 is the lever. We have a fulcrum and an effort and a load. That's a lever. Scissors are an example of a lever. This is the effort. This is the fulcrum where it pivots, and the load is in here, whatever I'm cutting. Here we see 2 pieces of Lego, pivoted at one end, moving in an arc. If I change where the pivot is, then it's still, both ends are moving in oscillating motion, but it's quite useful now and it's sometimes called a lever. If I had something heavy to move, this will do it for me. The reason is that my hand is moving a lot further than this. It's called mechanical advantage. So if I move the lever right down here, now it's making it harder to move the wheel. This end is moving much faster than this end. Number 5, the pulley. Number 6 is the screw. This worm drive is an example of a screw, and so is a wood screw. Let's talk about linkages. If I need Lego Lady to move up and down when I move this one across, then I need to link them somehow, and it's called linkages. This is the input and this is the output that I want. Notice they're both pretty much linear motion. Okay, so what we're going to use in this situation is called a Bellcrank. So this is the Bellcrank. It's kind of an L shape, and if this is where I hold it and my input moves left and right, which we'll call horizontal, then the Lego Lady is moving vertically up and down. Pretty cool. There's so many different types of linkages, you wouldn't believe it. So here's a close-up of the Bellcrank. You can see it really is just an L-shaped piece, that being the pivot, and it changes motion 90 degrees from input to output. Next type of linkage. When I have the input moving to the right, I want the output move to the left. So I want them to move opposite each other. Can you imagine what sort of linkage? Okay, here we go. I've got a lever and I'll click that on both ends. Now, when I move one way, Lego Bad Guy moves opposite. Pulleys. Imagine you have to spin this little flower around and around. I could spin it from underneath. I could use an electric motor. I could couple those two together with some sticky tape and that would spin around. But what about if my input is linear or in a straight line? I'm going to need a crank. Now I'll connect a linkage and you can see that my linear input gives circular motion output. Cool. But what about if I can't quite reach there and I need to have my input way over here? No problem. I'm going to grab a belt and put around the two pulleys. Now you can see that my linear input gives circular motion output, but further over. So that's the cool thing about knowing about all these bits and pieces. Let's say we need the flower to spin much slower than the input. Maybe because I've got an electric motor. Motors spin very fast, but they're not powerful. How I do that is to use a smaller wheel at the front, even spinning straight on the axle. And you can see now that when I spin that one, the flower spins much slower. That's a great trick if you're using electric motors. What about if I'm spinning it by hand and my hand isn't quick enough? I want it to spin a lot quicker. Just use a smaller pulley on the other end and now it's spinning much faster than the input. Pulleys can also change the direction of motion. Because belts are flexible, the two pulleys are now turning in different directions. Gears are really just wheels with little teeth around the circumference. If this is my input, the output will be much slower. If I turn it around the other way and make this my input and this my output, now you'll see the output is spinning much faster. A ratchet is a gear that will only spin in one direction. Let's say I wanted it to only spin this way and not back again. So I use a lever, which is called a pawl, a ratchet and pawl, and it'll spin this way, but gets stuck if I try and move it backwards, as long as this is touching here. So the trick is keeping the pawl on the ratchet. I could do that with maybe rubber band, and as long as that's pulled down onto there, forwards, not backwards. Yeah. Some more gears. This is a worm. It's like a gear that's wrapped around a shaft. If I place it alongside another gear and spin it around, the gear spins super slowly. And the reason is that every time the worm moves all the way around once, the cog only moves forwards by one of those little teeth. So if there was 20 teeth around there, it would be spinning 20 times slower than the worm, which is perfect if you want to reduce an electric motor down to something that spins a bit more slowly. You'll notice the worm drive also changes circular motion from this direction to this direction, 90 degrees. Another gear that performs the same thing is a bevel gear. They're cut at 45 degrees, and so they go together like that and changes circular motion again from this direction or axis to this axis. Pretty cool, huh? You could achieve the same thing with something more low-tech, just some lumps around a shaft. When it engages with another one, we'll actually spin it around. The trick is having some really good bearings to hold them in place, because as you try and push, they tend to force themselves apart.